Hi, welcome to Mechanical Engineering 313. I'd like to welcome you to Lecture 1, Part 1. I am very excited to teach this class, and I want you to be excited about taking this class. But in order to be excited about taking this class, you need to know what this class is actually about. And unfortunately, with a name like Engineering Analysis, the course title doesn't really give you a lot of information about what you'll be learning in this course. So I'd like to spend this first lecture, lecture number 1, kind of giving you an overview of what this class is actually about. The best place to start to learn what this course is about is, of course, to look at the course syllabus and the official course description on that syllabus. So if you look at your course syllabus, or you go online to our department's website and look at the official course description for this class, you will learn that in this course, you will learn how the analysis and modeling of engineering problems utilizing numerical and mathematical techniques and computers. Now, I strongly suspect, having read this course description, that you are still not excited about taking this course. And you're still probably somewhat confused about what this course is about. So let me give you my more unofficial version of what you'll be learning in this course. My definition of what this course is about, at least the way I teach the class, is that this is an introduction to a technique called finite element analysis for finding approximate solutions to ordinary and partial differential equations. In this class, we're going to focus on problems modeling the deformation of solid objects under an applied load, because it is those class of differential equations that we as mechanical engineers are most interested in, and it is the class of problems where finite element analysis is mostly used in mechanical engineering. Now that you know my unofficial definition of what this course is about, I suspect you're still not excited about taking this course. So let me give you yet another definition of what you will be learning in this course. In this course, you will be learning an introduction to a technique for using computers to predict the future. Focusing, of course, on predicting how solid objects will deform under an applied load, but the techniques you'll be learning in this class can in generally be used for predicting the future and using computers to make those predictions for us. Now, you've heard me use the word differential equations quite a bit, and I know that's a big, scary word. And I know that the term differential equations probably doesn't excite you as much as it excites me. And I suspect the reason is because of the two different types of differential equations courses that an undergraduate can take, you've probably taken the first type of differential equations course. In that first type of differential equations course, this is how I define differential equations courses. This is only me. I say that differential equations courses fall into two categories. The first type, which I suspect is the type that you took, is a course where you learn what a differential equation is. You learn how to classify differential equations into ordinary differential equations and partial differential equations and linear differential equations and nonlinear differential equations and first order and second order and third order differential equations. You learn how to solve some simple first order linear differential equations. You learn how to solve maybe some second order linear differential equations. You might learn a few techniques that work to solve a certain class of nonlinear differential equations. You may even learn that if you can make some simplifications to your problem, you can maneuver and manipulate your differential equation to a form so you can solve it using this technique that works just on this very small class of nonlinear differential equation. But that type of class that's very rigorous doesn't actually give you a lot of information about what differential equations are, how they're used, the beauty of differential equations, and how we use differential equations as a tool. There is another type of differential equations class. Differential equations class type 2 is where you learn how to model with differential equations. How you learn to look at the real world and take simple observations about the real world and write those observations down in the form of a differential equation. Where you learn some graphical techniques and try to get a good visual and conceptual understanding about what differential equations are and how they're used by mathematicians and scientists to model the real world. And then by solving those differential equations, we are in fact then able to use those solutions to make predictions about future behavior. Since I suspect that many of you have taken the first type of differential equations course, I want to spend a little bit of lecture number 1 discussing and giving you some demonstrations of how we mathematically model the real world using differential equations. So you can see some of the power that differential equations gives you and how you can use the solutions to differential equations to make predictions about the future behavior of a system or a part of the world that you've modeled with differential equations. Before I do that, there's 3 things about math I want you to know. 3 secrets about math that you may not have learned in previous math courses. The first is that math is an art. I know you probably don't think of mathematics as an art. You probably think of mathematics as a very rigorous set of rules that must be followed in a certain way. But mathematics is really an art. And there are sometimes in mathematical modeling, you need to make creative choices about how to take the real world and model it mathematically. Mathematics is an art. And we'll learn some aspects of that, and we'll use some aspects of that in this course. The second thing I want you to know about mathematics is that contrary to what the impression you may have gotten in previous math courses, is we as humans don't actually know all there is to know about mathematics. We don't know all of the solutions to all of the mathematical problems out there. Particularly when it comes to differential equations, it turns out that we as human beings are only able to solve a very small subset of differential equations. Now, just because we don't know how to solve them doesn't mean that we don't know that there are solutions. And even though we don't know how to solve a differential equations, we can, through numerical techniques, come up with approximations to solutions to those differential equations. And that is a big chunk of what this course is about. Thirdly, what is math all about? Why do we take so many math courses? What is the point to mathematics? And this is something nobody ever tells you. And nobody told me. This is something that occurred to me well into my graduate studies. What is math all about? Mathematics is a tool for predicting the future. That's all math is. It's a tool for making predictions, typically predictions about the future. If Sally has 2 apples and Fred gives her 3 more apples, how many apples will Sally have? It's a prediction about the future. And if all you know is algebra, then all you can do with your predictions is predict the countable, measurable world. But once you know calculus and once you have the concepts of differential equations under your belt, you're able to model the real world in ways you couldn't before by modeling how one thing changes with respect to the change in something else, which is all a differential equation is. So I would like, since I suspect that many of you have taken this first type of math class, to spend the rest of lecture 1 giving you some examples of how we can take the real world and model it as a differential equation, and then solve that differential equation to be able to make predictions about the way the world and systems we model behave. And I'll start that up again in part 2 of lecture 1.